This is the second part of the lecture on reliability and validity. So just some quick slides discussing validity. As we looked at in the beginning of this lecture, the concept of validity is muddy. It's mired in this very old historical tradition of psychometrics that involved a lot of correlational evidence. There's many different names for many different kinds of associations that one could look at. And then, as we talked about, there's sort of a shift now to this new way of thinking about validity. And the most important pieces of that new way of thinking about validity are, number one, that it's a property of interpretations and not a property of instruments. And that number two, we might do away with a lot of those individual descriptors of what kind of validity analysis we're doing and rather just think carefully about the kinds of evidence that we could collect that might speak to the validity of the inferences that we make on the basis of scores obtained from testing instruments or measurements from testing instruments. But I do want to say a little more to that point, which is as far back as Cronbach and Meehl. So Cronbach and Meehl are considered the scholars in the 50s who spearheaded the idea of using correlational evidence to establish that a measurement device measures what it purports to. Again, they were talking about self-report instrumentation specifically in the psychological context. And they said, well, there's a weak and a strong program. The weak program is just a fairly haphazard collection of correlational evidence that you could use to support construct validity. I have been specifically avoiding giving different types of validity assessments their own descriptors because they're not consistent, and but in any case, pretty much everyone will appreciate the notion that construct validity is what we're talking about when we say, does an instrument measure what it purports to measure? Does it tap the construct that you think it does? That's construct validity. There is a very real sense in which all correlational validity assessments to some extent speak to that, right? So predictive validity, or the ability of an instrument to predict scores on the same instrument or a related instrument later in time, or a behavioral correlate, is also construct validity, right? And so if you see typologies of measurement validity, as we said in the beginning, if you look online, and everyone has a different typology, a different way of categorizing and organizing them, but they probably all try to point in the same direction. They point at this notion of construct validity. So Cronbach and Meehl said there's the weak version of that, which is the haphazard collection of correlational evidence. But as far back as when they really kicked this research program off, they said there's also a strong program, or a strong version of that, where you would apply Popperian principles or formulate correlational hypotheses about how things should be related that could be falsified, right? So instead of collecting confirmatory evidence by saying, oh, it should be related to this and it should be related to that ad nauseum, it's a much stronger test to say it should be related to this, but not to that. And that was the beginning of the idea that you would try to collect disconfirmatory evidence. And that's where these ideas of convergent and discriminant validity came from. Again, I don't want us to get hung up on the particular expressions, the particular words, or the way these things are labeled, but just to recognize from kind of a higher level that it's nice to have hypotheses about how things should be related. It's nice to have multiple observations at the same time, at some future time, and it's nice to have hypotheses that some things should be strongly related and some things should not be related. And when Cronbach and Meehl were doing this work, they didn't have access to the kinds of computing power that we have now that allows us to do these things all at the same time in really sophisticated statistical models. Let's go. So this is the criticisms of that way of thinking about construct validity are many, and that's much of what Michelle says, right? And my sense of it is that Cronbach and Meehl knew that. We talked about in a previous class the idea that the way that these typologies and systems of validity were established was a preemptory attempt to guard against the notion that there is no validity, right? Because if all you have to rely on is correlational evidence of my measure against a gold standard measure, then the question of what was that measure validated against another gold standard measure, and so Cronbach and Meehl in the beginning were trying to say there's a black hole at the end of that. There's an infinite regress, and so the way that they conceived of it, and the way it is still practiced till now, is that attempt to guard against that. So now in modern measurement theory, in the stuff that we've been looking at in this class, we've been talking about this notion that things are a measure of what they are a measure of simply because they are, right? Because it's silly to imagine that you wouldn't know what you were measuring when you went out with your measurement device. Denny Borsboom says the reliance in classical theory on correlation is absurd because the implication is that a test measures whatever it's correlated with. And then I've given you guys this example in class before. If you are trying to build a test of, numerical ability, calculation ability, numerical reasoning, you might choose the item 2 + 2 =? Why would you choose that item? Because it correlates with something else that you think also measures the same thing? No, you would choose that item simply because it just is a measure of the thing that you're trying to measure, because you knew beforehand, right? You went in with a strong theory of the realness, the existence of the thing, numerical ability that you were trying to measure, and that you, through some means that we're not really talking about in this class, mapped the conceptual space of what that trait looks like. What should people who have high numerical ability be able to do? Well, they should be able to solve this problem, right? And then you used the indicator, not because it correlated with something else that you thought would measure the same thing, or correlated with future behavior on addition tasks, right? No, you used the indicator because you knew a priori that it was a measure of what an indicator of the underlying phenomenon that you were interested in. So that's what we've been sort of talking about the last few weeks, is this idea that validity is an ontological question, not an epistemological one. So if you go way back, I think to day one, we sort of took up these terms and talked about what they mean. To say that validity is an ontological question means that it's a question about the existence of things, right? That's what we said ontology means. It's the study of what's real, what exists. Validity is not an epistemological question, which is to say, it's not about the way we come to know things, right? Which is what epistemology is. It's the science of knowing, how we come to know things. So that quote at the top, validity is an ontological question, not an epistemological one, attempts to sum up that position, that validity should be a more reasoned approach to establishing reality, or that it's not about how we come to know what's real. Okay, so having said that, I want to look a little bit at structural equation modeling. There's just a few slides because this is not a structural equation modeling class. We'll see this again when we talk about confirmatory factor analysis, which is a part of it's an application of structural equation modeling. But I don't want to underestimate again how important structural equation modeling was in helping scholars to develop all of these ideas. So let's think about how we might use structural equation modeling to talk about validation. So this figure is a structural equation model. It should not look overwhelming to you because we've been talking about these concepts all term. The ovals are unmeasured variables or latent variables. The squares are measured variables. The arrows indicate that the latents are causing, or whatever's on the non-arrow side is the cause of whatever's on the arrow side. And this represents, this could represent a lot of things, right? This could represent a number of self-report measures. The indicators could be observations. The indicators could be scores from a future measurement, scores from a past measurement. This is a complex one. So this one, in addition to saying that these underlying variables have indicators, which they do, this model also says that the latent variables are related to each other in causal ways. So this is not here because we're going to talk about this particular theory. This is here just to show that there are a tremendous number of calculations that have to go into something like this. All of the indicator errors have to be estimated. All of the latent variable variances, all of the path coefficients that go on every line that you see. This doesn't posit that there are covariances among the latent variables, but it could. And so you can see that, prior to having a really powerful computer, no one could have done this. And then when we started to get powerful computing and it was recognized that a figure like this might do well to capture something around simultaneous correlational evidence for validity. So as we just saw, this idea that it would be good if we could get some hypotheses like, this measure should be positively related to this other measure. It should not be related to this other thing, and that we could literally physically draw on a piece of paper a diagram of what we expected those relationships to look like. And then now we're in a position to statistically estimate them. And so that's why structural equation modeling was seen as such a welcome addition to the toolbox of folks who were thinking about validation, was because you could not only conceptually specify those hypotheses and those relationships, but that you could then statistically test them. Structural equation modeling simultaneously estimates all of those things given nothing more than, remember, if you look at this diagram, the only data that went into this statistical estimation are the squares, right? All you start out with are the observed variables. And so structural equation modeling, maybe you're coming to see, is this incredibly powerful technique because you start with just these observed variables and then you estimate everything else from the data from the ground up. So you'll notice one thing that's true here is every latent variable has its own set of indicators, right? Positive affection has 3 indicators, negative affection has 4, service quality has 3, utilitarian value has its own hedonic value, satisfaction, word of mouth, those things all have their own indicators. So there's no latent variable here that isn't operationalized or by its own indicators. Another thing I'll say here is if you just took one of those latent variables, one of those ovals, and its own set of indicators and got rid of everything else on the screen, you would have a confirmatory factor analytic model. You would have what's called a measurement model. If all you have is a latent variable or several latent variables, but this one set of indicators, then you have what's called a measurement model. And on that measurement model, you can perform a confirmatory factor analysis, which we will be doing later in the term. Here's a one that's probably a little more consistent with what we're talking about in terms of the validation of instrumentation is think of intelligence as a latent, right? Which, we're kind of getting the nitty gritty now because we're saying, oh, I think this is a real thing, right? I'm sort of committed to the proposition that this is a real underlying trait on which people can differ in a continuous manner, right? The nature of the variable itself out in nature is such that it's continuously distributed. We all possess some amount of it, some T amount, right? And I believe that the indicators of intelligence are these 4 scales, scale 1, 2, 3, and 4. These could be whatever. These could be the subcomponents of one of the widely used intelligence tests. The little arrow that's doubled over at the top, you don't need to worry about. That's just another expression of how to draw error on a latent variable. So it's the same as having a circle with an arrow. So if you wanted to validate your intelligence test with these subscales or these measures, you might say, well, I think, intelligence should be strongly associated with academic performance, right? And so you would then have these additional three indicators, SAT score, high school GPA, and ACT score. You would use them as indicators of academic performance. And you would dump all 7 of those observed variables, scale 1, scale 2, scale 3, scale 4, SAT score, high school GPA, and ACT score. You would sit down and draw out this model. When you drew the model to begin with, right, there would be no numbers there. You are just plotting conceptually what you think the model looks like. And then you would estimate from the available data these coefficients. So in this particular data set, and this is also not my example, I just snatched this from the internet, but this is a reasonable test of validation. If you hypothesize that intelligence should be highly related to academic performance, well, what we get is a coefficient of 0.8. And we're also simultaneously sort of testing the hypothesis that SAT score, high school GPA, and ACT score are good indicators of this underlying variable academic performance because their correlations are very high with the latent 0.98, 0.75, 0.87. And you're also testing the hypothesis that the 4 scales that you've got are reasonable indicators of intelligence because they themselves are highly correlated with the latent. So I think, I only wanted to present these kind of models to you to get you thinking about the fact that you should always sit down and draw out these hypotheses, right? Thinking about latent variables, thinking about their existence, thinking about whether the model is formative or reflexive, thinking about what good indicators of that thing should be, drawing out expected relationships among latent variables. If we wanted to make this very strong, we might posit something that intelligence should not be related to, right? Like, I don't know, ability to, shear a sheep, or right, shearing ability overall. We could collect some indicators of that. We would sit down, draw out the model, and then we could test that hypothesis, simultaneously test the hypothesis that intelligence is a strong predictor of academic performance, but a near zero predictor of shearing ability. That obviously is a silly example, but that captures the idea of how you can use these modeling approaches to think about validation. And it's an incredibly strong way to do it. Okay, so that's it. These are some references that I think are good that I've dropped in here. Messick is really good. Zumbo is really good. So these look kind of old, right? But they're talking about modern validity theory. Okay, so I will see you guys in a week, and I hope you are all doing very well.